devices in 2020. Okay. So, MediaKind, my company. You all know that MediaKind is Ericsson Media Solution, which we spun out February 1st. Ericsson spun out its Ericsson Media Solution. So myself and Mario and Ronaldo, we all worked for Ericsson. And in the case of Mario and I, we go back to Tamper Television before Ericsson bought Tamper Television. I've been with the company now through 3 different names for 15 years. I guess Mario, you're up on over 20 now, right?
Yeah.
20 years. So our company, we have a big research thing for compression. We're one of the world's leaders in compression and media processing. And we did some of our own studies in our lab using what's known as a reference model, because it's really hard to compare these things. We have our own implementation of real-time encode that's done in both software and real-time encode that's done in hardware. But it's hard to compare that against a reference model of somebody else's, because you'll get an unfair comparison. So you have to do apples to apples comparison. So the reference model for 81 versus a reference model for HEVC. And we have a whole paper that was presented to the SMPTE Annual Tech Conference last fall that describes this. This is taken out from that. What the difference could be. So the objective, in summary, I mean, I gave some of the numbers here, but in summary, 81 can achieve better code efficiency over HEVC by about 10%. Great news, right? 10% can be significant, particularly for 4K. But here's the issue. It's 72 times slower. So it's not real time. That's why there's no 81 real-time coders out there. You can decode it in real time, you can't encode it. Whole class of operations can't do it. Yet, they're getting better. But it's because to make it royalty free, they can't do certain things, and they did other things to try to make up for it. And it's really, remember that I told you, it's a trade-off between coding efficiency and complexity in the code. We tried to match the conditions as best as we could between them. So it is reasonable to say that. If you go on the web and you look, there's a whole set of people arguing over this right now. Like one group saying 81 is nowhere near as good as HEVC, and the 81 group, AOM, which is the users group that does 81, is saying, oh, we blow away HEVC. It's because they're doing unfair comparisons. So the best we could say is that it's 72% slower, 79%, sorry, no, much worse than that. It's 72 times, so 720%. So, 50 times. That would get 10% better efficiency. So they don't look the same. And this is where it comes down to users looking at it. So in the sequences, it really varies very much. This is not PQ, perceptual quantization in HDR. Fortunately, there's ambiguous terms. This PQ, picture quality. It's or image quality. They call it IQ. It's picture quality. It's very much content dependent, but because of how they differ, in all likelihood, most consumers aren't going to be able to tell that 10% difference at all. Here's some examples of this. Again, we pointed out for you. What I wanted to basically say was, as an overall statement, 81 sequences are less sharp. They're more blurry, less sharp. When we talk about high dynamic range, what does high dynamic range rely on? Sharpness, contrast, right? It's less sharp. That's how they're able to get the bit rate down, because they're smoothing things out, so the resolution is lower, right? But that being said, HEVC is sharper, but then it suffers from blocking and ringing artifacts. And blocking is, I think you guys all know what blocking looks like. You know what a ringing artifact is? When you look around at something that's moving, you'll see like it looks like a ring, but it's a reflection of what's being coded. So depending on your sensitivity, you might prefer one versus the other, or might not see either. Most professional video people like myself, we prefer sharper pictures with ringing up to a point. If it gets so blocking and so obvious and annoying, you don't like that either. Versus softening the picture to the point where you're not looking at it, it's not 4K or HD or all this stuff. Okay.
Can you improve that?
Yeah, you can adjust the coder, but to make it less blurry, blocking, it takes more complexity, right? So, I'm pointing this out, we're trying to get to real time, to real time applications. If you have all the time in the world, any encoder can be made to work with, right? If you just keep re-encoding it until you get it. Okay, just to show you about this, so MPEG-2 was 1994, and at that point in time, if you were gonna do HD with that, it'd be about 20 megabits per second, you have bit rate reduction, you got complexity. When they moved from that to 2003 to MP4 ADC, it was basically half the bit rate, okay, for the same picture quality. In order to do that, the encoder was 8 times more complex and the decoder was 2 times more complex. Now, it happened to be that in that 10-year time frame, because of Moore's law, electronics getting better, being able to do things more in parallel, this was not an issue at all, not an issue. Again, go back to HEVC, which was just put out in 2013, another 50%, so now what used to take 20 megabits per second with HD is only 5. These numbers are all about, you can do HD at 10 with MPEG-2 or 5 with ADCs. This is not as good, but I'm just picking numbers. Another 50% reduction. In this case, 10 years later, it was 10 times for an encoder and 3 times for a decoder. But again, because 10 years went by, multiple generations, it wasn't such a big deal. Here's where the problem comes into play. Between 2013 and 2019, AV1's come out. It's 10% better, so 5 goes to 4.5. Right? Get right there, 10%. But 72 times more complex than code. And the reason why it says 1, it's just really not the same as HEVC is. This is why I can do it. This is important to keep in mind. We're going to keep improving it, but it's just not where it is right now. So, commercial coders, as I said before, always trade off bit rate reduction for computational complexity. It's a fact of life. As a matter of fact, it's actually a triumvirate. It's a triangle of things. It's bit rate reduction, computational complexity, and latency. How long it takes you to get the result out. The simplicity of this is bit rate reduction. So HEVC is commercial right now. There are multiple vendors out there, including MediaKind. And you can also get open source, something called X265 and SVP HEVC are out there right now. For AV1, for the commercial aspect of it, there are several vendor implementations in process right now. You can get them, Socionet, NG Codec tutorials, so you can actually get it from them. Or you just go to the OEM, again, the AOM library. AOM is the name of the industry forum that's doing this. The library is called LibOEM. You get it, it's open source, so you grab it off the web. And they also have the one from Mozilla, and Intel also has their software video coding, which is really wonderful as well. It's getting better. From December of last year until February of this year, they went from 32 minutes per frame to 1.5 minutes per frame. I don't think you're going to get that type of gain again. I think something must have happened when somebody figured something out. But implementation improvements, you disable certain tools in certain places, so they're getting around it by shutting them off. So they're not getting the efficiency, right? That's what we're talking about. They're adding some shortcuts in, and they're trying to do something for multi-threading, doing things in parallel. For those that know, great. If you don't know what this, if you know what wavefront encoding is, HEVC does it quite a bit. So in parallel processing, do lines of the coding in the screen in parallel. We used to not be able to do that. So it is getting better. But I just want to make sure we point this out. So still, this is bit rate reduction, and this is factors of encoding time. If you take a look at ABC commercial, it's real time. And that's our baseline. We're going to call that 0. Okay? If you go to these software versions of AV1, if you want to get them near 0, you do get over ABC, 30% about right there. HEVC commercial is about 40%. Again, these are almost real time. As time goes out, right, you can see AOM over AVC is 60% more efficient. It's fantastic. But as time goes down, you're seeing a trend here. What's happening? the efficiency is going down, so like 45% here. And obviously, we take this, it's about 10% difference. So the jury's still out which way to go on this. But here's where you might see AV1 being used. So you have file-based for like, video on demand or content on demand, catch-up TV, nice little catch-up TV. But this is the thing the most converged is real-time linear. Because if you're going to do a converged head-end, which I'll talk about in the topic later on today, then you want to use one format for everything. So for traditional broadcast TV all the way down, it's going to be very unusual to see AV1. Where you're going to see AV1 coming out of streaming services, which is what you'd expect, because what do those guys do mostly is streaming services. So probably about a year's time, we'll see more of AV1 coming out. Commercial encoders, as I mentioned earlier, will be out towards the end of the year. Performance is unclear. In other words, what percentage efficiency versus making it over what period of time it will be. I don't know what that is in that. Streaming services for real-time linear, maybe in a couple of years. It's really hard to predict this because it really depends on traction. It absolutely, AV1 is going to be used, just like it is now. We have WebRT environments and stuff like that. It's just whether or not it is able to actually get any interest in that. And let's make it even more complex, because is it really just about HEVC versus AV1, or is there something else out there? There is something else out there. It's known as VVC, versatile video coding. That's where that's from. Those are from the people that brought you HEVC, AVC, and MPEG-2. They haven't been sitting back either. They're already ready to come up with things called versatile video coding. It's the next generation of that group. The schedule, there's a call for proposals in October 2017. October of 18 years later, they did a final selection of the test material so they can evaluate it. And then they're going to have a 2-year period, which they're already in now, for people implementing that. And they're going to test it against the test model. And the first release of the new standard will be in October of next year. So it's just under 2 years away. If you want to learn more about what's going on, because we don't want a repeat of the disaster we had with IPR licensing for HEVC, a new industry forum finally got smart and said, we can't do this, or we're putting ourselves out of business. This is my personal opinion. It's not MediaKind's, but my own. If HEVC didn't have this disaster of a problem with IPR, there wouldn't be an 81. Because it's just, there's too much momentum behind open standards development. Anyways, 32 organizations responded to that, including our predecessor, Ericsson. There were, obviously, the results were based on the new tools that are available now. That actually was a clear subjective and objective benefits that go beyond HEVC. And it ranged anywhere from a 44% gain, which is almost half the bit rate again, right? With 13 times the encoded complexity in decode times, to about a 30% gain at 2x encoding. 2x encoding, again, that's an easy thing, right? The coders. So this looks like a real winner, BVC. But again, it's too premature to know what it's going to be like. So, I know not everybody here was interested in this topic, so thanks for putting up for those that weren't. For those that like this topic, any questions before I go on to the next one, which is this. Okay, here we go again. So, good job, you weren't interested. I hope it was worthwhile. At least you guys know about HEVC now and AV1, and hopefully a little bit about VVC. Last topic for this section, updates on adaptive bitrate streaming, okay? So, does everybody here know what adaptive bitrate streaming is, ADR streaming? Okay, that looks like most people here know. Good. So, hard to believe that just a few years ago, this was a toy. You know, over the top stuff, video, and if you didn't get the hourglass or juddery pictures, you were all excited to look at something that had pretty much no resolution. It was like sub SD resolution, it really wasn't covered that well, right? And again, sometimes you're trading off just being able to get anything is the art glass versus using AVR different profiles to get back and forth. But that's changed now. So we have live TV channels are all over the place on the web now for over the top and across a lot of devices on here. The underlying technology for all the over the top stuff is one of the adaptive bitrate technologies, AVR. Now, most of the modern AVR systems are all what they know as HTTP based. I'm assuming everybody here knows what HTTP is. And that's been pretty much developed. You have your traditional broadcast head end, and then you have your over the top. It could even be two different sets of people that are working on it. A lot of times, the over the top comes from your IT department and broadcast department is the other. But if you're cable, direct broadcast, satellite, digital, terrestrial television, or if you're an IPTV provider, you can't do both. But this is the thing, most operators are now considering simplifying that. It looks like this, you can take a look at what we have for our MediaKind, it's the same thing. But if you take the best broadcast quality profile from AVR, you can use that for broadcast television. It's that good now. Whereas a few years ago, it wasn't. So that's what a lot of people say, well, wait a minute, if the profile is that good, I can use my broadcast profile, why can't I converge the whole head end and only have one head end? When I say head end, it could be studio broadcast facility, just use the word head end. So that's where the next generation AVR is really going. It's all about having a unified head end. And it's really, if you take a look at that, there's three areas and the reasons why you want to do this. You want to reduce investment and simplify operations. Why have two teams of people delivering video? Rather have one unified team. Wouldn't it be great when you want to make adjustments that pull-down screens for the encoders all look the same? Shouldn't matter whether it's over the top. Over the top should be just a delivery mechanism. It shouldn't be how you code it. So you don't want to have separate silos. The next thing is, we want to go for this, is everything is about personalization. You want to move a target, an advertisement, or make something relevant, or use analytics to make sure the stream is working. So you want to have a single ad insertion architecture targeted. The nice thing about AVR, as you guys know, is it's fixed packet sizes. So it makes it a lot easier to do ad insertion or program substitution because you just pull it as a chunk and pull it out and replace it completely. As opposed to, which what makes it difficult, trying to do an encode boundary at an iframe or something like that. And the other thing is, you can actually expand a service that you don't even offer now. And most content providers doing this now, they're offering their own over-the-top service. They're not doing it through somebody else now. So people that used to be on Netflix, for instance, aren't necessarily on Netflix now. They're doing their own services because they can go off net. They already have the content because they produced it for their broadcast quality, right? And they're sharing the same one. So why not do this? And this is to get a purely over-the-top set-top box, or let's think about this. Or no set-top box. It just goes to a client that plays on a PC or a smartphone. We need a set-top box. So the end goal for the next generation AVR is same or better than broadcast AV across all devices. Very important. That's the work across all devices. You're looking for the target, the user advertising and placement. You want to minimize bandwidth and storage optimism and strategies for doing that. And of course, you want a quality experience for that playback. You don't want that jumpy screen. You don't want people worrying about which thing it is. If you really want a universality, right, you can be watching it on the big screen TV in your home, and you decide you're going out. You pause it there. You want to be able to pick it up on your mobile device, and it'll be completely seamless with the whole thing. So often, grab the content and play. That sounds great, right? That's a lot of work to make that seamless with all the different user experience. That's the goal. So, as I described a few minutes ago, it wasn't that long ago, first generation AVR, where you really were limited by very low picture quality. It's not enough to look at this as a toy. But more importantly, the latency. In many cases, it was up to a minute delay. And that's no big deal if you're watching a movie. How would you know? It takes a minute to start it up in the beginning, and then the buffer keeps getting full, right? So you just start a minute late, who cares? You watch the movie. Well, it does matter if you're watching live sports, particularly if you're betting on live sports, right? Or if you're in an apartment building, and you're really into this big World Cup game, right? And you hear your neighbor go, yeah! Something happened a minute later, it shows in your screen. That's not exactly a good user experience, right? Yeah. So we really got to get this down. It's traditional broadcast. When you say broadcast quality, we're talking very high quality video, like very watchable, no question. It's HD or better, and it's circa or under 2 seconds latency. So it's a big difference from 2 seconds to 60 seconds, right? So in order to address the high quality issue, a lot of work has been done. And again, if I had more time to talk about it, I could spend a lot of time talking about constant video quality processing, something that we do. Really, we don't do things constant bit rate anymore. We actually vary the bit rate, but leave the quality constant. It uses less storage capacity, sometimes up to 30–40% less, and frees that bandwidth to do that. So we're addressing the picture quality. So that's pretty much done. But the end-to-end latency, we really need to work on that to be a significant barrier for doing that. And I already mentioned this. It's real-time gambling, the synchronized second screen apps, where you got something you're watching on your big screen, but you're doing a different view maybe on your tablet. Like if you're watching this work game, you do that. Maybe like Formula One racing, like you can do a track, you have a track overhead, or you have your favorite driver, and the camera's in the car driver, things like that. So there are 3 new technologies to address ADR latency that are out there now. I'm going to spend the rest of this section on. There's something known as CNAP, Common Media Application Format. In particular, it's LLC, low latency coding. You all know what hypertext transport protocol is. There's a version 1.1 for this. It's called chunk transfer encoding. Get into the chunk kit. That's the technical term for the PC cutouts, chunk. And then Dash, which is the dynamic adaptive streaming over HTTP. It's an MPEG standard. There's an extension to support the chunk transfer here. All these 3 things need to be used together. So, just in case you don't know what CNAP is, okay? CNAP, or Common Media Application Format, was invented to finally get all the formats for adaptive bitrate streaming to the line. That's what Dash was supposed to do. And then through practical application, there was 2 different profiles for Dash. And Apple went one way with the transport stream, which is no surprise. That's what HLS is. That's Apple's HTTP live stream. It's basically a MP2 transport stream. And everybody else went with the MP4 file format, basically file format. So CNAP is a way to bring Apple back in a compatible way for themselves. So it's another file format. It is based on the base media file format, which is part of the MP4 way back then. What it really does is you have a segment, which is the different ways you have things that are put into the internet framing for that. It allows them to be broken down into smaller chunks. And those chunks can be used as a transport mechanism. Everything else usually works the same. I'll get a better picture from this. I'll show you something. Again, the whole point is the conversion now between Dash and HLS. You say, again, the second attempt to get HLS into the fold. And now you have the manifest and the playlist share fragments, which is the first time you ever happened to. So now you have that the Apple and the Dash playlist share the same fragments in the common format, but all the FMP4 based. So that was a concession that Apple made that was compatible to it. It's good news now, because now you can share the cluster. So the point behind this is, now your encoding is done once in one format. That's the convert 10N right there, one format. You have an adaptive transport stream of something that goes into a packager. This is what's new. The packaging and the encryption is done once now. It used to have to be done at least twice in different systems. All right. And then the manifest is delivered to Dash devices, or playlists are delivered to the HLS devices. But the packaging and the encoding is the same one. And they're identical. The fragments themselves are identical, but also this has never happened before. So this is really a very powerful thing in the for doing that. So let's look at this for a second. So the media chunks, which is how, again, how you start encodings. The existing way of doing it, you go an intraframe to an intraframe. I know that not everybody here does compression. If you don't know what this is, don't worry about it. For those that do, you know, there's, the IPP and IDR frames, right? So it had to be an intraframe. So it had to be either an I-frame or an IDR frame to do this. Okay, all the B frames and P frames and 3 frames, you couldn't do this. You know, wait, because that could be a half a second, that could be 5 seconds. That was your, or 10 seconds. That was your chunk size. So think about it. It's 5 or 10 seconds long, and that's your chunk, and the device can't do anything on the receive side until you get it. You just introduced what? Chunk size times 2, because you can't empty the buffer delay. That's why it's 20 or 30 seconds delay. Just running that one section just before you can start playing. That's what we're trying to work on to get rid of that. In the case of the new smaller chunks, the segment stays the same. You're not changing the segment. So all standard AVR coders, decoders, all work the same way. We're not changing the fundamentals here. You're allowing the fragments to be sent early without waiting for the whole thing. So there's not this latency. And the other side buffer knows what to do with these fragments and can actually start decoding a fragment before the whole segment comes in. That's how you get rid of latency. Does that make sense? That's the secret behind this. It never thought you could do this because they never thought to get it formatted. So a movie fragment is known as a move. I think most people know that. And then the media data is MDAT. Those are the names that if you see it in the industry. So working along with that, this is CMAP LLC. Okay, being able to do this. Working along with that, it changes the hypertext transport protocol for chunk transfers. Okay, in the old days, it did this. You got the packager would take the camera, push it in the segment, it would be encoded, they could push to an origin server, and the client would request it. Okay, I could wait all this time. Now, with the multi-fragment ones, it does them all at once and sends them out. So it's allowed to send multiple fragments out at the same time. So doing serially. So basically, this is the big thing. The server can reply with the content, and the client never, it's a pull system with AVR. Client requests content. Instead of waiting for the entire fragment, that's small chunks instead. Okay? And it doesn't need to even know the full data or the size of the file. You can just start sending the chunks. Doesn't matter anymore. And this is really a way of over the network now reducing the delays. Now we have smaller fragments and device knows how to do it, and now we have a mechanism to transfer it faster without waiting. And the last thing is both HLS Apple files and Dash manifest. In the case of Dash, it's known as a media presentation description. It's a manifest file. Basically, does everybody get on a manifest file? It's basically a link to the chunks. You read this like a directory file. You read this, it goes, okay, I need this piece for this file, this is named, and this is where it's found. That's how you can do it. Program substitution. All you can do is change that one line manifest and point to something else instead. Boom, you have the program. That's why add insertion is so much easier to do. So normally you'd have to wait for the start time of each segment. Everything's done by segments. Now you can do it by fragments instead. So the clients don't have to wait for that whole time. Now they just do it through a fragment. And there's a new parameter called availability time offset. So you can send the segments over here. With no start. Normally you wouldn't do that. You'd wait until the whole segment was received, then go. Here you're just going to start right away. Again, the client can start preloading it without waiting for the whole thing. Now, it does assume, of course, that clients know how to do buffer management. That hasn't gone away. It's standard AVR, so that's what we mean by progressive download. You have to have progressive reception segments and manage your own buffer. Otherwise, you'll, just like in the old days, you'll run out. So, if you take all this together, we're going to convert head end with low latency over the top delivery. Using TCP/IP, for instance, it starts as an MPEG-2 transport stream, encoded stream. Encoding live, that's the our encoder that does this, but it could be anybody's live encoder does it. We then produce two things. We're going to produce out of the same encoder a segmented MPEG-2 transport stream file. So it's still an MPEG-2 transport stream, but it has all the prep that's in it. So you can divide it up into chunks and fragments and segments, right? You take the TCP multicast, and that's your IPTV one, your standard IPTV or cable or whatever you want to use. Multicast, but in the other case, you segment it and then goes into the low latency packager and origin server. The output of that is then in CMAS format, and that's what the device will do an HTTP get for the packet for that. So you get both same things, but it will play in an IPTV set box, the low latency player. The whole point behind this is these are supposed to be running at the same time, whereas before this could be a minute behind. That makes sense? This is pretty powerful stuff moving forward. It's actually bridging for the first time we can really envision a converged head-end. How many people here are familiar with ATSC, which is the U.S. and actually not U.S. It's North America and Korea's terrestrial television system? They just came out with 3.0. For the first time, they're not using the transport stream as their native format. They're using IP packets. So you can see the converging is already starting to happen. Now, as one of the writers and creators of the MPEG-2 transport stream, I was one of the 20 people that wrote MPEG-2 systems. I guess we had a good run, total 5 years, but it's still out there, not going right away. But it's just showing you that you can unlock the power of IP. That's what the next section after we take the break. Talking about unlocking the power of IP. It's not IP itself that's important. It's all the things you get to do because you're leveraging an IP environment. And that's what this is all about. Now what happens is, when you do all this stuff, it's a standard IP network. You're not inventing new protocols, not proprietary interfaces that you have, or industry-specific interfaces. Okay. Any questions? I keep you attracted for that time. It was about just under an hour and a half. I guess. Go ahead.
The first slide, do you mean with
multicast? What's that? Oh, TCP. What's TCP multicast?
Yes.
Okay, so there is a new mechanism now where you can actually set up to do multicast based on. It's actually, this is shorthand notation. It's actually UDP multicast, but it's TCP. It gets converted to TCP. So it comes in as TCP and it goes out as UDP. You can go back and forth with it. Yeah, I skipped that piece. Sorry. So it's a way of being able, you convert back and forth between the two. So you can take all the advantages of multicast, but you have the assured delivery of TCP. Does that make sense? I did skip that whole thing. All right. Good question. See, I'm not a perfect presenter. Any other questions on this? Again, interesting topic. Cool stuff. Now you know what CMAP is. Now you know LLC. This is all the new cool stuff. Just went through all the new cool stuff. Maybe not all, but a lot of the cool. I'm sorry, say that again? Yes. Yes, doesn't matter if you use H664, which is also known as MPEG-4 or if you use HEVC or AV1 or the new DVC, that all include that. Now, obviously, whatever you use has to be understood by the receiver, right? But the packaging itself is completely independent of the coding. That is a great question. Very important to understand that.
Matthew, can you talk a little bit more about the client side? What is the kind of client, what is the kind of change you should have on the client side?
Sure. So the goal behind a lot of this is not to change anything on the client. It's all hidden from the client. It's standard ADR stuff. It's all done up here. And some of the stuff that we're doing here with this is with TCP multicast, is to fake out the client. It thinks it's getting the standard multicast, but we're actually doing more things with it. The idea is in the network, being able to do all these type of optimizations, yet it's a standard client on the other end. So the only thing the client needs to be aware of, obviously, is it has to know CMAP. Okay, that's new. But as far as how it does its progressive downloads and packets and how AVR normally works, it still works this way. Now, one thing that's not directly related to this, but abuse is, if you're on a managed network, you can control your traffic. So one thing you can do, like for instance, if you're an IPTV or cable operator, you own your network, you could actually offer a service that says, when you see over-the-top content from Netflix or Amazon, if you go over our network, it will look better. Because what you're really doing is you're doing these clever tricks up here. This client doesn't know any difference. It thinks it's just requesting packets from the network. But you're actually metering, controlling the network management a lot better up here. And I could do a whole hour just describing all the really clever things you do that. I think that might be where Ronaldo was coming out. The cleverness up here. You could have it actually, a managed network can make your over-the-top experiences better now because you play games by controlling the bandwidth to make sure the bandwidth isn't bogged up. But the client doesn't know this. The client just sees standard packets. The only thing that changes the client again is that it has to understand, obviously, CMAP because that's unpacked. But it's still the same HTTP, well, it's new HTTP. So it's still like, yeah, but
Yep. You are still presenting the client many profiles in order to have a program in the network to change profile and do.
yeah. So there are still many different profiles produced depending on the network availability and how the client's requesting it, right? So that's why you can use fewer profiles or manage your network. That was the whole network optimization stuff we were talking about, that being the network be optimized. But yes, the concept of profile still exists where you might have requested a 4K program. And if the network is clear, you'll get the segments that match the 4K, which would be the highest bit rate that you're offering and the best resolution, best frame rate, right? Your next profile, something's gonna give, right? You're gonna have less bandwidth. So typically what you do first is you leave the frame rate up because you want pitches to look like the way pitches. What do? You lower the resolution. And you do it at the segment boundaries so that even though you requested 4K, it might only be HD if the bandwidth's not there. But the goal behind that, as of course you'll adapt the bit rates for, right, is that it's seamless. It will go softer for maybe 20 seconds and then go stronger as the different segments are able to be set. So all that's the same. So you definitely have to have multiple profiles. But the goal is if you manage the network better, it gives a better opportunity for the client to get the higher profile. That's the goal. So you get a better user. That's what I mean about claiming, hey, you get a better user experience if you do over a managed network. Is to clear enough bandwidth in the network and manage that network so you're getting the higher profile. Right? Does that make sense? Yeah. Okay. Yes.
In a managed network, what is the lowest latency that you can achieve with the state of the art in the managed?
Well, that's a hard question to answer, but it could be down the same as what it would be for regular IPTV. So you're looking at 1 to 2 seconds.
Okay. Even using encryption, I mean, what is the state of the art right now?
Yeah, even with encryption.
Okay.
Yeah, for the live encryption, yeah. It's pretty good. I mean, internet itself doesn't really have that much delay. It all depends on the server boundaries at this point in time. Clearly, if there's no bandwidth at the end of the day, you're not going to get repackaged, right? But even satellite itself is what, 1/4 to 1/2 second for satellite transfer, right, Mario? Yeah. 1/4 to 1/2 second for satellite transfer. So you're never gonna get down to 0. I mean, you're always gonna have something. But even with you can do real-time encryption of it. So it's only when I say real-time, it could be a couple of frames delayed, but it's 50 to 100 milliseconds.
Okay.
Does that make sense? It really, when you're doing that, though, I hope it's clear that you're using hardware assist to do that encryption. It's not all pure software, right? And most people to get rid of that latency are doing a hardware, well, sometimes a CAM, module that will encrypt in real time. So keep that, because you're right, if you don't do that, you can add 10 seconds just for that. But most people that's a known doable thing you can do with a hardware accelerator, whether it's an FPGA or floating point accelerator, graphics. GPU.
For the staffing, you have something, let's say, complicated because you need to initialize differently the player or something like that, or it's transparent. I mean, do staffing between CMAP services and
Yeah.
say regular dash.
Right. The client needs to know it's, the client, the difference is it has to use. Oops. This is the difference. The client needs to implement the dash extensions, still dash, but it's a later version, right? It needs to do HTTP 1.1, so it's still HTTP, it's the later version. There's nothing proprietary, these are all the same protocol. And you have to do the CMAP, otherwise, but all the other functions of how AVR works is exactly the same. It's just that if you don't know that you're receiving, chunks instead of, segments, fragment, I should say fragment. I keep using the word chunk, sorry. It's an old habit because it used to be called that. It's called fragments now, sorry. It needs to know that it's not, if the request is being made, instead of requesting the segment start time, it's now the fragment time. So it is a later version, but it's all code, it's all standard code. But it doesn't need to do anything special regarding its buffer fill strategy, which just is requesting that they know it's CMAP based. Because like I said, it's almost identical, you can see, but it's just the parameter has changed to be the fragment instead of the segment. Anything else?
In your view, this solution is ready to be deployed? I mean,
Yeah.
is it deployed or it's still standardized way?
Well, I mean, you always have to do network optimization, but as far as these technologies, they're ready to start playing with them now. That's one of the advantages of doing IP-based protocols like this, is you try it out, and you actually try it out in your live network. If it doesn't work, you roll back. I mean, it's not like you do a rollout of 5 million set-top boxes, right, and it doesn't work, it's broken. This is all standard software stacks. So that's one of the advantages. You try it out. This is Netflix not as much as Amazon, but Amazon oftentimes they'll roll out something new for a day and go, oops. they roll back the old one right afterwards. Because they can. What better way to test out your strategy than with live users, right? People seem to be a heck of a lot more forgiving than they would if they were, paying the equivalent of $100 a month for television service that they have. Right? I'll try to get to that. But yeah, you can start to deploy this stuff. In our equipment, if you're going to do a MediaKind, I believe we'll have everything done with this by the end of the second quarter. I don't have the exact, you probably know this better than us.
Yeah, correct.
And we'll have all the pieces together ready to go in a production format in the June. So the reason why I'm here in Ohio is because typically the way we do it is we're working with us, we'll give you beta code up to 3 months before that if you want to be a beta code.
It's part of the packaging revolution.
Yeah. Again, other than mentioning that we have this, I wanted this to be, this isn't a product presentation, this is a technology. But we do have this.
So in your view, makes sense use HVC for a while, or the marketplace, they start to see HEVC 81 and another codec like a BBC.
If I were launching now, I'd be using HEVC. That's what I'd do.
Because the standard not ready, so the challenge from the processing,
With 81,
yeah.
yes, it's not ready yet.
It's a perfect question, so.
Well, what it comes down to is the application. 81 is coming, but it's more for like a web browser type of experience. So if you're doing like a YouTube thing, or using a flat video, but not for linear television, at least not yet. A couple of years, again, listen, I mentioned it earlier, if they don't resolve the licensing issue, all bets are off, right? I mean, did this with ABC, 15 years ago. The level of commercial stubbornness by some people is just, it's outstanding. Thank you. Anything else? Stopping you from your break? It's 11:45. I'm gonna make the executive order, which I have no power to do. So like, Jose can override me if he wants to. But if we can be back here at 12:15, I'll do the next, I'll give you a chance to rest my chops and you guys can absorb the myriad of excellent information that I gave you. Thank you, everybody, for sitting with me.